Hey everyone and welcome. Today we are jumping right to the absolute bleeding edge of technology. We're going to explore a truly visionary idea that could completely reshape, well, everything. From the phone in your pocket to the car you drive. We're talking about what happens when two giants, quantum computing and edge AI, finally collide. So, let's get into it.
So this whole thing kicks off with a really powerful statement from edge AI strategist Fani Bhushan-Athar. He's painting a picture of the future, right? One where the incredibly strange and powerful rules of the quantum world start solving the biggest problems we have in our tiny smart devices. It is a bold claim, for sure. So let's break down what he means.
All right, so before we can really appreciate the quantum solution, we first have to wrap our heads around the problem. And it is a big one, something Fani calls the edge paradox. It's this fundamental tension that's right at the heart of all modern computing.
I mean, just think about it for a second. We are cramming incredible intelligence. We're talking small language models, TinyML, onto the smallest devices you can imagine. Your smartwatch, your smart home assistant, tiny sensors out in a factory. All of them are running on insanely tight power budgets, we're talking milliwatts, and they only have kilobytes of memory to work with. We're basically asking them to do magic with almost nothing.
And this is where it gets really tricky. Our good old classical way of building computers, it's hitting a wall, a literal physics wall. You try to pack more power in, you just get more heat, more delays, and you drain the battery in no time. All things that are total deal breakers for a tiny edge device. And that leads to this huge question. What if we're going about this all wrong? What if the answer isn't to just keep shrinking the old way, but to embrace something completely different? And that something different is, you guessed it, quantum. Now, to really get what makes it so revolutionary, we have to go right back to the beginning. We need to look at the most basic building block of all information, the bit, and see how quantum just completely rewrites the rules. Okay, so on the left, that's the classical bit. We all know it, we all love it. It's like a light switch. It's either off, a 0, or it's on, a 1. Simple. But then you look to the right, and you've got the qubit. The quantum bit doesn't have to choose. It can be a 0 times a 1 at the exact same time, living in this weird world of probabilities. This isn't just a small change. It's a massive expansion of what one single piece of information can even be.
So, this magic trick has a name, superposition. And as experts like Santanu Pattanayak help explain, it's not like the qubit is secretly one or the other and we just don't know. No, it genuinely is in this blended state of both possibilities. It's only when we peak, when we measure it, that it snaps into place as either a definitive 0 or 1. Before that moment, it's holding way more information than a classical bit ever could.
But wait, there's more. Superposition is really just the beginning of the story. The true mind-bending power of quantum computing comes from a couple of other properties that let qubits work together in ways that are just flat-out impossible for classical computers. First up, we have entanglement. You might have heard of this one. It's what Einstein called spooky action at a distance, and for good reason. When you entangle two qubits, they form this deep, unbreakable link. If you measure one and find out it's a 0, you know, instantly, that its partner is also a 0, even if it's on the other side of the galaxy. It's a connection that creates correlations that are way more powerful than anything in our everyday world. Now, this might sound like some kind of space magic, but it's actually done through very precise steps using things called quantum gates. Let's just walk through a really simple recipe here. You start with two boring qubits. Then you hit the first one with a special gate that puts it into that both 0 and 1 superposition state. Then a second gate links the two, basically saying the fate of the second qubit now depends on the first one. And boom, just like that, they are a perfectly correlated, entangled pair. It just goes to show how these amazing quantum states are built with logical, repeatable steps. Okay, the second secret weapon is called interference. Because qubits exist in a state of probabilities, they can act kind of like waves. And just like sound waves, they can add up, making the probability of the right answer get louder and louder. That's constructive interference. Or, even cooler, they can cancel each other out, making all the wrong answers go completely silent. This is literally how a quantum algorithm sifts through a mountain of possibilities to find the correct one so efficiently. Okay, superposition, entanglement, interference. That was a lot of weird quantum physics. So what? How does any of this actually solve that real-world edge paradox we started with? Let's connect the dots. This slide right here, this is the whole shebang. This is where Fani Bhushan-Athar's vision really comes to life. Superposition? That lets you do massive parallel computing, checking tons of solutions at once in a microscopic footprint. Entanglement, that's your key to compressing AI models exponentially, way beyond anything we can do classically, so they actually fit in those tiny memory budgets. And interference, that gives you ultra-efficient optimization, so you can find the best answer without burning through your battery. See? Each quantum property is a direct solution to a huge bottleneck in edge AI.
So where does all this lead? Well, it's not about throwing away all our current technology. The vision is actually way more practical and, honestly, a lot closer than you might think.
Yeah, the future isn't some quantum phone that replaces the one you have now. Instead, the vision is all about hybrid devices. Your normal classical processor will still be there doing its thing, but it'll be boosted by a tiny, specialized quantum coprocessor working alongside it.
And they're each going to play to their strengths. The quantum processor will take on the jobs it's uniquely built for, those super complex optimization problems, that insane model compression, and creating unbreakable security. Meanwhile, the classical chip just keeps on doing what it does best, running standard programs and all the day-to-day operations. It really is the best of both worlds working together inside a single device.
So just like Fanny Othler says, this isn't science fiction anymore. The math, the principles we just walked through, it's all here. The big challenge now is really about the engineering. And that leaves us with this one, final, really provocative question. How long until this kind of hybrid power is sitting right there in your pocket? The next frontier, well, it might be a whole lot closer than we think.